Section 2.2, it's a second derivative test. Second derivative test. What is second derivative test? What is it about? Well, first thing is you are given a function f of x, you find f prime of x, and from there you get fw prime of x. That's called the second derivative. Second derivative of f of x. So the condition is that if f is continuous, whose derivative f prime exists at every point in its domain, then when the second derivative bigger than 0, this means the graph concaves up. The graphs of f concaves up. Concaves up means, it's gonna open upward like this. That's concaves up. It's like a U shape. If the second derivative is less than 0, the graph of f concaves down. This is called test for concavity. Test for concavity. Also, good to know or introduce, when is the function increasing? How does it look like? Increasing means, it's always from left to right. There are two options. Either it goes this way or it goes this way. In both of them, that's when the derivative is bigger than 0. That's what increasing. But the difference between them, the first one concaves down and the second one concaves up. That's what it is. Theorem. This is what's called the second derivative test. Let f be continuous. F prime exists over the domain of f prime, and f has a critical value c. Do you remember critical values? If you don't see the previous sections, critical value are the value or values when we said that the derivative equals 0 or does not exist. So over the domain of f prime, f has a critical value c in, let's say, the interval ab, for which f prime at c is 0. Then this is what the test says. This is what the test says. If fw prime of c bigger than 0, then f of c has a relative minimum. If the second derivative at c is less than 0, then f of c has a relative maximum. Graphically, what does that mean? For the first case, so it says the second derivative bigger than 0. This means it concaves up at c. And remember, at c, the derivative is 0. So it's like this. This is c. At this point, there's a horizontal tangent. That's what this is saying. Horizontal tangent. Horizontal tangent at x equals c. There's a horizontal tangent here. And based on the first condition, it concaves up like that. This tells us at this point that I'm going to mark in red, it concaves up, and it's a minimum. It's a relative min. Same situation for the fact when it's down, concaving down. So at C, there's a horizontal tangent and it concaves down, then there's a max at that point, relative max. Let's look at an example now. Let f of x be the function given in the form x cubed minus 12x minus 1. Find any relative extrema min slash max. Then check for concavity. Check for concavity. Always to find minimum, maximum, we need to find the critical numbers. That's the first step. So find the critical numbers. How do you find the critical numbers? From previous sections, we have the function x cubed minus 12x minus 1. We need to set the derivative equal to 0 for polynomial functions, which is 3x squared minus 12. If you set that equal to 0, you can divide everything by 3. And to solve this, we factor x minus 2, x plus 2. We get x equals 2 or x equals negative 2. Those are called critical numbers. We can find their corresponding y values. So if you find f of 2 and f of negative 2, you substitute into the original function. And if we calculate f of 2, we get negative 17. This is negative 2 to the third minus 12 times negative 2 minus 1. That's a 15. Now, these are critical numbers. Now, at these critical numbers, we don't know, there's going to be a relative min or max, but we don't know if it's a relative min or max. How do we do so? We can find the second derivative from there, which is 6x. And we are going to check the second derivative at these two numbers, at 2 and at negative 2. And let's see what we get. Is it positive or negative? So the second derivative at 2 is 6 times 2, which is 12. That's a positive. Next one, 6 times negative 2, negative 12, negative. This means f has relative. By the second derivative test, it says if the second derivative at the critical number is positive, there's a relative minimum at x equals 2. F has relative max at x equals negative 2. Okay, so now if we want to put this on the number line, if we want to place this on the number line, so if we put this on number line like that, we have a negative 2 and a positive 2. These are the only critical values we have. And this is the number line for the second derivative. If we pick a testing point, say x equals 3, substitute into the second derivative, that gives us a positive. If you pick something in between, say x equals 1, that's going to give us positive. At 0, in the middle of that, at 0, here, when you pick x equals -1, that's going to be negative, and that's going to be negative. So this concaves down, concaves down, concaves up, concaves up. So what happened here is it's concaving up below, down below 0, and above 0, it concaves up. So what happens is, from the second derivative that we found, if we set it equal to 0, that would help us to solve for x equals 0. And if we substitute into the original function, that will give me -1. So when x is 0, y -1. This point is a special point. It's called point of inflection or inflection point. Inflection point. Very important to know this. So, okay, so we move on. And let's take what we have so far and graph it. Try to graph this function. So 0, -1 is a point of inflection. That's where the graph changes concavity from up, down, or down, up. So it's going to go through that point, 0, -1. Also, we have critical numbers 2, -17. So 1, 2, and say -17 here. And we have -2, 15. So at these points, there's horizontal tangent lines. Okay, and I'll show you what that means. Based on our work so far, below 0, it's concaving down. So the only way to go through these 3 points is to have it this way. So the graph is concaving down over this interval, and concaves up over this interval. So based on the critical values, based on concavity test or second derivative test, point of inflection, I was able to sketch or run a sketch for the graph like this one without the use of calculator. Let me add a note. Let me add the note to find the coordinates of inflection points. We set the second derivative equal to 0 or does not exist. That will give us what we need. Now we're going to look at another example similar to this. X cubed plus 3x squared minus 9x minus 13. So you're going to find the critical numbers. You're going to find when is it increasing and decreasing. Discuss concavity. Sketch. So let's go over this question. We start by finding y prime. That's the way to find the critical numbers. 3x squared plus 6x minus 9. and we need to set this equal to 0. Notice that all these numbers, 3, 6, and 9, are divisible by 3. So if we divide everything by 3, we get a simpler equation that is factorable. X plus 3, x minus 1. And you can test it. From this, if you set each one equal to 0, x would be -3 and x would be 1. Those are the critical numbers. If you want to find the critical points, means you want to find the y values, the corresponding y values, just substitute into the original. You get -27 plus 27 plus 27 minus 13. Y would be 14. For this, you will get 1 plus 3 minus 9 minus 13 into the original function, remember. So we have a point -3, 14, the graph is going to go through, and 1 comma -18. And what does that help us? I can check when is this function going to be increasing, when is it decreasing. I see -3 and 1. Those are the critical numbers. This is the number line for f prime to check about increasing, decreasing. If I pick x equals 2 and substitute into the derivative, into f prime, as you can see here, into f prime, it will give us positive. If you pick x equals 0 into f prime, negative, x equals -4, positive. So increasing, decreasing, increasing.
Professor.
Yes.
So wouldn't it be -1 as your critical number, and then +3?
No, because when you set them, you said x plus 3 is 0, x minus 1 is 0. So you subtract 3 on both sides, you get this one. Add 1 to both sides.
Oh, got it. Thank you.
So now we learned before something called first derivative test. We say by the first derivative test, when the sign changes from positive to negative, there's a relative max. As you can see, at x equals -3. When the sign changes from negative to positive, there's a relative min at x equals 1. That's by the first derivative test. It tells me exactly if the points at these critical values are relative min or relative max. And the other way to do it, the one we learned today, is by concavity test or second derivative test, actually. Second derivative test. So let's find the second derivative. We get 6x plus 6. If you set it equal to 0, subtract 6 on both sides, then divide by 6. From this, substitute this into the original function, and I got -2. So that tells me that the point I, -1, -2, is an inflection point. Not only that, the second derivative to tell me when does the graph concave up, when does it concave down. So if we find the second derivative, sign bigger than 0, that's when the 6x plus 6 bigger than 0, 6x bigger than -6, x bigger than -1. that's when it's going to concave up. The second derivative less than 0, that's when x less than -1 concaves down. So this is the second derivative. Here, concaves down, concaves up. Now we're going to graph it. What do we have? We have a point 1, -18. Say it's here. There's a critical point. We have -1, the point -1, when x -1, y -2. Say here, that's an inflection point. And we had a -3 and 14. Say 14 is there. Notice it says below -1 concaves down. So concaves down is going to go like this. Then it concaves up. Notice how it concaves down. Then up. And you can test the increasing, decreasing. It says it's increasing below -3 and after 1. And notice it is below -3 and after 1. It's increasing in these cases and decreasing between -3 and 1. We're going to run through another function, one last function, x plus 1 to the 2/3. How do you find the derivative for this? Y prime, bring the 2/3 down and subtract 1. 2/3 x plus 1 to the -1/3. I can rewrite this by bringing the x plus 1 to the 1/3 down. When is this going to be 0? That's how we get the critical numbers. Either equal to 0 or does not exist. Equal to 0, you get nothing, because if you cross multiply, you get 2 equals 0. But 4 does not exist, that's when the denominator is 0. That's when x equals -1. So this is called a critical number for the graph. Call this f of x, the original function. For when x is -1, y would be 0. So you got a -1 comma 0. That's the only critical number we have. We can run a number line for the first derivative. So if you pick a point here, say x equals 1, and substitute into the first derivative, you can see it's going to give us positive. If you pick any point below -1, say -2, that's going to give us a negative. So it's decreasing, then increasing. Okay, copy that down. So we now find the second derivative. Back to the first derivative. It was 2/3 x plus 1 to the negative 1/3. The second derivative, you bring the negative 1/3 down and subtract 1. Negative 2/9 x plus 1 to the negative 4/3, which can be rewritten as negative 2/9 x plus 1 to the 4/3. Now the second derivative equals 0 or does not exist only when the denominator is 0. So when x is negative 1. When x is negative 1, we always substitute into the original function to find the y value, which will be 0. So then x is negative 1, y0 is an inflection point. Is an inflection point. And to graph this at negative 1, 0, let's see what happened. It's decreasing below negative 1 and increasing above after that. So decreasing, it could mean like this or like this. Now, how do we tell which one? One of them is concaving up, one concaves down. So that can be done by checking the second derivative. When is it bigger than 0? Bigger than 0 when x bigger than negative 1. So it means it concaves. Oh, concave. No, actually, no. The second derivative bigger than 0, that's when negative 2/9 times x plus 1 to the 4/3 is bigger than 0. If you multiply by negative both sides to kill that negative sign, less than 0. When is this less than 0? When the denominator is less than 0, when x less than negative 1. So it concaves up when x less than negative 1. And it concaves down otherwise. Note the function, if you reviewed the previous sections, it's not differentiable at this point. There's like a what we called cusp. It's a cusp. Last question, try to sketch a graph for the function f with the given information. F is increasing and concaves down on negative infinity to 1. F is decreasing and concaves up on 1 to infinity. Try to sketch a graph for this. Sketch the graph based on the following conditions. First thing, it's increasing. This is the point 1. Increasing and concaves down. So it doesn't have to be exactly at that point. It could be up here, could be here, could be anywhere as long as on the same line as 1. So concaves, increasing, concaves down, it means like this. That's what increasing and concave down. Okay, that's increasing and concave down. Then decreasing and concave up. So after that, it's decreasing and concave like that. See, This one is increasing, is going up and concaves down. Then concaves up and decreasing. Decreasing means it's from left to right. We're drawing from left to right. Any questions about this? So again, you need to go back and review how you find derivatives. Make sure you know what critical numbers are, when is the graph increasing or decreasing, and first derivative test. That was taught in previous sections. Now in this section, we learned the second derivative test that tells us about if the critical number or if the function at that critical number has a relative min or max. And we learned the concavity test. The concavity test says if the second derivative bigger than 0, the graph concaves up. If it's less than 0, the graph concaves down. Anyone has any questions?